Let's wait for 2 3 minutes. Then I will start. Okay, we can start. So, so this is the week 12 problem solving session. So today again our plan will be to start with first the assignment question for week 11 that we will solve in detail, and after that we will move to the week 12 content and mostly focus on the generalized linear models, and mostly the week 12 assignments are based on the exponential family of distributions. So we will touch upon this and we will solve some practice questions based on that. So these are the topics we will be doing today. So there is another thing that is nonlinear distribution model. So we will talk about that in the uh, next week problem solving session. Okay. So at the beginning, I will start with this uh, the assignment questions. So let's start. All right. So let's look at the first question. So this is the week 11 assignment. So first question is that suppose we have n observations on response variable y and predictor variable x. We plot the scatter plot and judge that the relationship between x and y is nonlinear. And we want to fit a polynomial regression. What should be the order of the polynomial? As we know, we have discussed it in the last lecture, that order of the polynomial regression should be as low as possible. So particularly one of the order is given as, so for the first question, let me write, for polynomial regression, the order of polynomial should be as low as possible. Particularly if you want an estimate, it should be k from less than equal to 2. At max, second order of polynomial. You can go for third order of polynomial, but after that, it is not a good uh, model to solve for this regression analysis or some kind of a fitting. Okay, so therefore, in the polynomial regression model, order of polynomial should be as low as possible, particularly k less than equal to 2, where k is the order of the polynomial. Okay, let's go to the second. Second question is consider the fitting of an orthogonal polynomial. We have done a question, practice question in the last lecture, where we have seen, particularly we have solved it, this orthogonal polynomial. So it will be an easy question after that. So, so this is the orthogonal polynomial regression model, which is shown here in the second question. That is y is equal to alpha naught p naught x, alpha 1 p 1, and so on, and I goes from 1 to n, and puxi is ux order polynomial, and x be the matrix corresponding to these orthogonal polynomials, which are we have seen. This is how it has to be represented. Question is that what is the variance of alpha j hat? Okay, so this is the question. What is the variance of alpha j hat in this kind of a model? Well, so alpha j hat for orthogonal polynomials. So we write for orthogonal polynomials or orthogonal polynomial based model. Alpha j hat is how it is written. So it will be a summation on I, yi, p of, you can write u also because it is given in the question as u. I am writing it as j, jth order polynomial, and divided by summation pj square x. So in the denominator, it is the summation of the square of the polynomial, jth order polynomial, and in the numerator, it is y times the, so polynomial weighted response, summation of that. Okay, so this is how we have seen that the alpha j hat is to be calculated. Now we need to find the variance of alpha j hat. right? This is what we need to find out. Right? So let's do it. So this is variance of alpha j hat, right? So we need to take the variance of what? Variance of this particular quantity which I have written here. So let me write step by step. Yn, which is pjx divided by summation pj square x. That's all. So we know that x, or the polynomial which is already in x, which is pj, it is on some kind of a non-random variable. X is a non-random variable. We have discussed in so many times in the last couple of lectures that x is a non-random variable. It's an independent kind of a variable. So therefore, you can consider here this x as some kind of a constant, not a random variable. Only random variable here is y. Therefore, variance must be applied on this y. Other things will be acting as a constant. And we know from basics of statistics, we know that variance of some kind of cx square, or say cx suppose, is nothing but c square variance of x. If this c is some kind of a constant. I have discussed it many times. Okay, so this is how the variance of constant times x can be represented. Now you can see here in this particular part, this is also a constant because it is a function of x, which is a non-random variable. Whereas in the numerator, within the summation, only random variable is yi, or on which this variance operator will be applied. But pjx is a function of x. Again, it is a constant. Therefore, we can write therefore this alpha j hat as summation. Let me write summation here. Variance of yi pjx can be now pj square because it will be square based on this. And in the denominator, this summation entirely can be squared, right? Pg square x is already there. Now we will square it because this is also a kind of a constant quantity because variance has to be applied on y because y is the random variable. X is not a random variable. Okay, so based on this, we can write this. Okay, what is now variance of y? Variance of y is sigma square. The summation sigma square, which will be same for all. So it will be pj square x divided by the entire thing which we have got. Pj square x whole square. Correct. So we get here sigma square can be taken out from the summation. This will be pj square x in the numerator divided by this will be summation pj square x whole square. Right. So if you look at the numerator and denominator now, this summation pj square x is present in the numerator also, and the denominator is square is present. So this summation pj square x and 1 from the denominator can be cut. So finally we get in the numerator it will be sigma square. In the denominator there will be 1 summation pj square. This should be the variance of alpha j hat. Alright. So this should be the answer. So this is the final answer. Sigma square divided by summation of pj square x. So let's see whether this option is present here or not. Uh, First option is summation pj x whole square. This is not the answer. If you come to the second option, you can see that variance of alpha j hat is sigma square divided by summation pj x whole square, which is what we have got. So this is the correct option. Okay. Now the third question is based on some kind of a data, and we have to fit some kind of a cubic model. Okay, but it has to be centered. See, centered about the mean. It is already given that it is x minus x bar whole square, and x minus x bar whole cube. So we have to calculate this and just simply solve it based on the multiple linear regression model. And we will get several of the questions after this. So let's do it. It will take some time, so we will do this. Okay, this is the third question, and third and After that, all the questions can be solved based on this. Okay, so let me first write that the model which they are asking for. So y is equal to beta naught plus beta 1 x minus x bar plus beta 2 x minus x bar whole square plus beta 3 x minus x bar whole cube. This is what is given. And you can see that this part is called the centering. Centering about what? Centering about the mean value of x, right? X bar. So this is the model which we need to fit. But whatever is given in the data, x, y, we have to convert it as some x prime. I will define what is x prime. This is x prime square and x prime cube. So x prime, I'm writing this x prime as x minus x. We can write this x minus x bar, just subtracting the actual value of x from the mean value of x. That is what we are trying to do. Okay, so let me just uh, write down whatever calculations has to be done. Okay, so let me write the data. Will take some time. So 1, 2, 3, 4, 6, 7, 8. So 18 observations are there. So I'm just writing, filling up each and every column. So 12, 13, 14, 15, 16, 18, 19. That is what? X. And okay, so now Y is 100, 90, 80, 60. Again, it will be 60, 55, 60, 65. Okay. Then 70. Next is again 70, 75, 76, 78, 79, 90, 99, 99 and 100. This is the Y column. And X prime can be calculated from the X bar value. Let me write what is the X bar. That is, you just add and divide by 18. So there are n is equal to 18 observation here. It is mentioned in the question also. Fine. So X bar is actually comes out to be 11.11. Let me write Y bar also. If you do the mean of Y, it comes out to be 78.11. Right? So I have to subtract each and every values of this X column from this X bar value. That is 11.11. So let us do and fill it up. Okay, x prime is represents x minus x bar and its squares and cubes. So I'm just writing one by one and filling it up. So it will be minus 10.11. This is 102.23. No negative sign because its square has been written here. But in cube, there will be some negative. Okay, so it's 83.01 minus 756.3. So you can do it roughly up to 2 decimal places or 1 decimal places, whichever is suitable for you. You can do it. Okay. So this is 65.79 minus 533.6. All right. Next, is so this will be 50.56, and this will be 359.5. Okay. I think this will be some minus will be there. Next is minus 5.11, minus 4.11. This is 26.12, 16.90. This becomes minus 133.52, minus 69.48, right? So next, minus 3.11, 9.68, and minus 30.11, minus 2.11, then minus 1.11. This will be 4.46, 1.23, and here it will be minus 9.4, minus 1.35. Further, you go, it will be 0.89. Just fill it up. Okay, so this is 0.79, 3.56, 8.34, and 15.12. A bit lengthy, this one, 23.9, and then 47.46, 62.23, 97.8, and finally 118.56. And at the last column, it will be about zero point 0.7 only. Since these are positive now, this x prime cube will also be positive. This will be 6.74 to 24.1, 58.81, 116.85, 326.9, 490.9, 967.03, and finally 1291.07. Okay, so these are the values of x prime square, and x prime cube, where x prime is this x minus x bar. X bar we have calculated, y bar also we have calculated. Now the simple thing is that you have to write the x matrix, because we will be doing the same thing. So we are actually, let me write here, we are reducing the model y hat is equal to beta naught hat plus beta 1 hat x prime plus beta 2 hat x prime square plus beta 3 hat x prime cube. We will be reducing this as the multiple linear regression model, where we are writing this as beta naught hat plus beta 1 hat from x1 beta 2 hat, this is x2, and beta 3 hat x. This is how we are going to reduce. In the same way we will be doing. So X matrix, there are 18 observations. So what it will be, first column will be always 1, corresponding to the beta naught parameter. Next is the x prime, all the values you have to write. Next x prime square, and next x prime cube. This will complete the X matrix, which will be total 18 observation as the rows and 4 columns. This is how your X matrix will be. Okay, I'm not writing the X matrix. You can see the above. This is nothing but the X matrix. From there will be one extra column of 1, and then x prime square, and x prime cube. Okay, so it's the lengthy matrix. I'm not writing it. So after this, what we can do is that we can calculate x prime x inverse. Let me write this x prime x inverse. So the process we know how to do it. So let me just write the inverse, which will be of the order 4 by 4. Okay, based on the parameters. Right. So let me just quickly write the values of the inverse matrix, which is 0.12233. As much as decimal places you should give it, so that you get the accurate answer. 0.01986. Next is minus 0.001646, and finally 3.56 into 10 to the power minus 5. This is how the first row of the inverse looks like. Fine. Next is 0.001906. It's a symmetric matrix, that's why it is repeating. This will be changed 8783 because it's a diagonal element. Next is 9.41 into 10 to the power minus 5. And finally minus 9.85 into 10 to the power minus 5. Fine. The third one is 86, you can write. Third one is minus point this one. This element will be repeated 001646, and the last one will be this one. So it will be 3.56 into 10 to the power minus 5. Fine. What about this one? This will be 9.41 into 10 to the power minus 5 and minus 9. This will be here 9.85 into 10 to the power minus 5. Well, the third one, this will be unique. It will be 4.089 into 10 to the power minus 5. And here it will be minus 1.5 into 10 to the power minus 6. This is also same. And finally, this is again a unique quantity because this is a diagonal element into 10 to the power minus. So this is the 4 by 4 x prime x inverse. So this is the inverse of the x prime x matrix. Okay. Now, another thing which we need to calculate is x prime into y. So you can do it easily because y column is also there in the data, and x prime can be calculated as a transpose of this. So it will be 4 by 18 matrix. So you can see that this x prime will be a 4 by 18 matrix. This will be an 18 by 1 matrix. So finally, whatever the result will be, it will be a 4 by 1 matrix. Right? So what is that 4 by 1 matrix that I will write? So x prime y is nothing but this. So it will be 1406 as the first element. Second is 740.777, 6541.0246, and finally 69023.96. This is the x prime y, which is a 4 by 1 matrix. Right? Now, we remember that from the multiple linear regression, beta hat, the estimate of betas actually is the matrix, can be found out from this x prime x inverse x prime y. Once you do it, you will get the beta matrix as this 65.304, 3.1798, 0.3273, and minus 0.0307. So these are the beta elements. So this is corresponding to beta naught hat. This is corresponding to beta 1 hat. This is beta 2 hat. This is beta 3 hat. So our model is now created, okay, based on whatever we have seen, how to do the polynomial regression model, just converting it into the multiple linear regression model like condition, and then solve for the questions. Okay, so fitting is being done. Now questions, let us see. Third question says that least square estimate of beta naught is equal to, then fourth question is beta 2, and fifth question is beta 3. We have already answered this. So let me go here. Therefore, for the third one, it says that what is the estimate of beta naught? So it will be beta naught hat, which is 65.304. Let me write, we will check. Fourth is beta 2 hat. They have not asked about beta 1 hat. So this is 3273. And the fifth one is beta 3 hat, which is nothing but minus 0.03. See, 0.7 can be rounded off to 1. Right? So it will be minus 0.031. So let's see 65.304, 0.327, and minus 0.301. Okay. 65.30 is right for beta naught, it is correct. For the beta 2, it is 0.327, which is the accepted answer. And for beta 3, it is minus 0.031, which also we have found out. Well, let's come to the next question, which is consider the data in problem 3. MS residual requires to be calculated. So let's see. This is completely based on the multiple linear regression model. Only the trick is that we are using the polynomial regression instead of multiple linear regression. But the way of proceeding is same. Okay, for the sixth question, they asked about to find out what is the MS residual. Okay, so for MS residual, what we require? We require SS residual and divided by the residual degrees of freedom. So what is the residual degrees of freedom? We know that residual degrees of freedom, which is the degrees of freedom for SS residual, is n, the total number of observations, minus number of constants. So constants can be because of the normalized equation due to all the parameters, unknown parameters. So how many unknown parameters in the model? So these are 1, 2, 3, and 4. So 4 unknown models, unknown parameters. So n minus 4. So the n is what? N is the total number of observation, 18, and 4 constants due to the normalized equation because of the 4 unknown parameters present. So 18 minus 4, which is equal to 14. So 14 is the residual degrees of freedom. Okay. Denominator is known. Now, question is what is the numerator? So SS residual needs to be found out. So we know that even without calculating all of these, we can calculate SS residual through a simple formulation y prime y minus beta hat prime x prime y, where this x prime y we have already calculated. Beta hat prime is also with us because beta hat is with us. Now y prime y is nothing but this is nothing but summation of y square. That's all. Okay. So you square the y and then add it. So let me give this value. This y prime y is because why am I writing this? Is because this is the matrix multiplication of the transpose and the actual matrix. That's why it will be summation of y square. Okay, this y prime y can be written as this 113778. So you can do one thing that you can square all these elements of y column and add it. You will get this answer. Okay, 113778. Okay, now beta hat prime x prime y. If you want to calculate, you can calculate. It will be about 113468.386. This should be the answer. Okay. So now the SS residual can be easily calculated. So SS residual will be what? It will be 113778 y prime y minus the beta hat prime x prime y. That is 113468.386. Now, if you calculate this, it will come out to be 309.6137. This is SS residual. What we require to find is the MS residual. So, MS residual is SS residual divided by the residual degrees of freedom, which is 14. Right? So, this will be 309.6137 divided by 14. That gives you 22.116 and can be written as 22.12 because 16 can be rounded to 2. Okay, so 22.12 is the answer for the MS residual. So let's go to the question again. Sixth question. Consider the data of MS residual. Yes, it is 22.12. Okay. Next, the seventh one is to calculate the MS regression. We have calculated MS residual. Now it's the time for MS regression. So let's go for the seventh question. So seventh question is to find out MS regression. Alright, so definition will not change. It is nothing but SS regression of the entire model divided by the regression degrees of freedom. Okay, so regression degrees of freedom you have to calculate. Well, uh, we can do it multiple ways. Let's go to stick to the definition how to calculate the degrees of freedom of the regression, SS regression. We know that SS total is nothing but SS residual plus SS regression. Right? For the SS total, definition will always remain the same because this will be y minus y bar whole square, which has one constant. We have discussed multiple times. It has one constant. So its degrees of freedom will be always n minus 1. SS residual degrees of freedom we have calculated n minus 4. Then what will be the degrees of freedom of SS regression? We know that degrees of freedom can be added, so you can easily calculate this. So this n cancels out, 4 goes this side, so d will be equal to 3, right? Because 4 minus 1 will be 3. So regression degrees of freedom. So degrees of freedom for SS regression will be 3. Correct? So this is done. The denominator part is done. We need to calculate now the numerator. Well, you can go ahead with the same definition that you calculate SS total separately. SS residual is already calculated. Then SS regression you will be getting. Okay. So this is one way you can do, or you directly apply the formula, which is nothing but the same. So SS regression can be calculated or formulated as beta prime x prime y minus n y bar square. Okay, so this is your SS regression actually coming from this one. So so we can this thing we already have. Can we just write it this? So 113468.386 minus n we have 18 and y bar we also have. We have also calculated y bar, that is 78.11. You square it and put it here. So if you square it and put it here, it comes out to be 6101 point something 345 something. Once you calculate everything, it comes out to be 3644.16. This is your SS regression. Okay. Now what we require is MS regression, which is nothing but SS regression 3644.16 divided by regression degrees of freedom, that is 3, which will give you 1214.72. This is the answer for the MS regression. So if you come to the question again and look for the answer, yes, it is 1214.72. Okay, and the last question is based on the hypothesis testing, which says that consider the data in problem 3. Now, given that SS residual for the model without the cubic term is approximately this. It is given that SS residual, if you don't consider the cubic term, is this. Question is that can the third order term be deleted from the fitted equation if alpha is 0.05 suppose? Then can this third order term be deleted or not? This is what the question asks. Okay, so based on the question, what can we write about the hypothesis? So it is given that your SS residual for the model without cubic term is 1033.08. This is already given. Okay, that means what? That means it is SS residual for beta naught hat plus beta 1 hat x prime plus beta 2 hat x prime squared. That's all. This model SS residual is given as 1033.08. Okay. Now SS total, which will not change if we change the parameters also, because SS total depends on y. Y is not changing. We are changing the x prime cube is not there. Okay, so it depends on y. This will not change. SS total, if we calculate, this comes out to be 3253.777. Okay, so how will you calculate? It's simple. You can either square the y minus y bar. So you can get into the definition of this yi minus y bar whole square, or you can do this, that you have your y prime y minus n y bar square. This actually is to this. This is matrix multiplication of y prime y minus n is the number of observation and y bar is the mean square. So in both ways, you will get this is the result of SS total. Okay. Let me find out what is the SS regression corresponding to that. It will be easy. SS total minus SS residual. Okay, this all things which we are calculating, this SS regression which we are calculating is the model without the cubic term. Remember. So this will be 3253.777 minus 1033.08. So this will yield, just a minute, this will yield to some 2920.69. So this is SS regression for the model without the cubic term. Therefore, you can create some H naught where you can say that beta 3 is equal to 0 or H1 where beta 3 is not equal to 0. If beta 3 is 0, if H naught is accepted, the null hypothesis is accepted, then in the presence of course, in the presence of beta 1, beta 2 and beta naught, okay, this will always be there. If beta 3 is 0, that is the null hypothesis is accepted, then we can delete the cubic term. But if it is not accepted, it is not significant, then or it is significantly different from 0, beta 3 is not equal to 0 in the presence of beta 1, beta 2 and beta naught, then we can say that no, it cannot be deleted. So this is the hypothesis testing corresponding to the question which is given. For that, we can use extra sum of square technique. F is nothing but we know that it is SS regression of the full model which we have calculated minus SS regression of the restricted model where cubic term is not there divided by 1 degree of freedom. You can understand that the full model has your 3 degrees of freedom and this will have 2. You can understand this. Okay, because only one parameter is not there. All right, so divided by the ms residual. This is also for the full model which is calculated. So f therefore for the full model what we have calculated is uh, for the full model is 3644.16. So let's write this will be 3644.16 minus for the restricted it is 2920.69 divided by 1. I'm not writing divided by 22.12. So this F you calculate comes out to be 723.47 divided by 22.116. You can clearly see that numerator it is very stronger as compared to the denominator. So giving a hint that 32.71 is a larger number, and if you compare, it becomes 4.60. If you this value is 0.05 1 comma 14. Why 14? Because this has degrees of freedom 14 we have calculated and this has 1. Okay, so this f is this and we can clearly see that the f statistic f value is much larger than this 4.60, which shows that your beta 3 or the cubic term cannot be neglected, can't be neglected or can't be deleted because it is significant, significantly higher than 0. H1 is accepted, right? So H1 is accepted and therefore cubic term can't be deleted. Therefore, if you go to the question again, you can see that can the third order term be deleted from the fitted equation? No. No is the correct answer. Okay. So this completes our assignment questions of week 11. Now we will go for the week 12 contents, which is based on the generalized linear models. We will not be touching today the nonlinear estimations. We will be only touching the generalized linear model and try to understand the questions which are associated to the with your week 12 assignment questions. All right. Now So before going to, so this is the week 12 content, first of all. So mostly the week 12 assignment questions are based on the exponential family of distributions. We will be seeing it very soon. And after that, we will try to practice some questions so that the assignment questions can be easily done. Just a minute. Okay. So for the week 12 contents, before going to the week 12 contents of the generalized linear model, let's go for a topic which we have done, uh, well, 2, 3 weeks before, week 8 or week 9, somewhere, which is generalized least square term. This is a topic which we have discussed where we have seen that suppose you have y is equal to x beta multiple linear regression model plus epsilon, and with some assumption, we generally do these assumptions, we do have these assumptions that the expectation value of this epsilon, that is this error term, is zero. We assume this always. And the variance of epsilon is actually from sigma square b. You cannot write, this can't be written as sigma square I. So this is therefore related to some kind of a non-constant variance, problem of non-constant variance. There we use this generalized least square technique. So there are many other things which we have discussed. That is, when observations, say y observations, so the response variable observations have unequal variance. Okay, unequal variances. We have discussed this in that lecture. And next is the observations are uncorrelated, or observations, sorry, they are correlated, cannot be uncorrelated. Observations are correlated. Okay, so these are the typical conditions where one must go for generalized least square technique, where we have seen that the weighted least square technique, we have discussed about weighted least square technique, and we have shown that weighted least square technique, we have shown that this weight is proportional to 1 upon sigma square. This also we have seen, and we have solved several questions. So this is the generalized least square technique. But what we today going to do is nothing but the generalized linear model. Okay, generalized linear model. This is what we are going to do in this particular lecture. Okay, so when these generalized linear models are required, so these conditions, let me write. So this generalized linear model, this analysis comes into picture when the error distribution, this epsilon which we are talking about, the epsilon or the error distribution, or your response variable distribution, because you know that error distribution, whatever the distribution it will have, finally, because there is a linear kind of a relationship which is present here, x beta plus epsilon. If it's a linear relationship, whatever the distribution of epsilon, same will be the distribution of the y, because x is not a random variable. If x will not be following any distribution, y will have a distribution which will be similar to that of the epsilon. Okay, so therefore it will come into picture when the epsilon, that is the error distribution, or the response variable, that is y distribution, is not normal, is not a normal distribution. Okay. It's not coming from a population of normal distribution. If this is the condition where the error distribution or the response variable y distribution is not coming from a population which is associated with the normal distribution, then only we will be going towards the generalized linear models. Also, there are other conditions like when a vector of non-linear, essentially the same thing, non-linear functions of response variable y exists and not the y itself. That means not y itself. So it is like this eta of y, which is so eta of y1, comma eta of y2, so on up to eta of y. And writing it as a transpose, you can write it in. Okay, and also it has expectation of this eta of y as your x beta, because this is just like what we do in the, so just as we do in multiple linear regression model, where we assume this y is equal to x beta plus epsilon. This is the model which we generally take, and we say that expectation of this y is nothing but x beta. Why? Because we assume that expectation of this error distribution is beta. That's why it will be x beta. Similarly, only difference is that this y will now not be the y itself, but it's some kind of a nonlinear uh, functions of y at present. And the error distribution or the response variable distribution should not be a normal distribution, should not come from a normal distribution. That is these are the major conditions. So the expectation of these nonlinear functions of y or the response variable should be equal to x beta. So that is what we generally consider here. Okay. Now, for this to do this generalized linear model, so in this GLM, I'm writing the generalized linear model, the response variable distribution must be a member of the exponential family. Okay. Now, fine. This is not a member of exponential family. Everything is fine. But if you look at the normal distribution, which we will be seeing very soon, we will be seeing this. If you look at the normal distribution, it will also have some kind of an exponential member. This is also an exponential member because e to the power minus x square something. That is the normal distribution. Then why we are using this? No, we will not be using this. You will find that ultimately in the generalized linear model, we don't require to use this generalized linear model technique. Link function will be similar. We will discuss all these things. We will see that link function is there is no change. You can ordinarily fit whatever we have done so far in the week 1, week 2, simple linear regression model, multiple linear regression, simple way we can do it. But except for the normal distribution, when error distribution or response variable are not normal, then we have to use some link function in order to fit the model. Okay, so this is the major concept for this generalized linear model. So before going to that, as most of our questions in week 12 uh, assignment are based on this exponential family of distributions, so we will try to look at different distribution and try to see how to generalize it as an exponential family of distribution, and we will generate a concept of canonical form, and then we will practice some problems because most of the questions are from that, almost all questions I will say, and then we will go for how to fit this generalized linear model, a simple brief introduction. For more insights you can go to the video lectures, there some details are there. Okay, so let's go for the exponential family of distribution. As we have seen that for generalized linear model, we require some kind of exponential family of distribution. The response variable distribution should follow or should be a member of exponential family. So let's go ahead with exponential family of distribution. All right. So what is the definition of this? Suppose a random variable, say u, and following the same notation which in the video lectures it is there, u that belongs to the exponential family with a single parameter theta will have or has a probability density function PDF as f of u comma theta. U is the random variable, theta is some kind of a parameter, as s of u, some function of u, some function of theta, into exponential of a of u, some function of u, and b of theta, where this s of u, t of theta, a of u, and b of theta, these are the functions of either random variable or the single parameter theta or the parameter of interest theta, are known functions. Okay, are known functions. So we can rewrite the above equation or the above PDF which we have represented here as f of u comma theta as exponential au into b theta plus some d function of u and plus some c function of theta. Can we write this easily? Because we are generalizing it. This is how we can write. If you take the exponential outside, you can take just the log of SU and just write it like this, right? So this is how we can easily generate. So what is this du therefore? Where this d of u is nothing but log of s of u and c of theta, not c, but t of theta, oh no, c of theta, sorry, is nothing but log of t of theta. Right. So these are the two. This is how we can generalize it within the exponential function. So this is how we can write uh, this exponential any distribution which follows this kind of a uh, function, which can be written like this. This PDF can be written like this. There we can apply the generalized linear model. Okay. Another thing is that when a of u is equal to the actual random variable, we say the distribution the distribution is said to be in canonical form, and b of theta is called the natural parameter. These are some introduction for this particular PDF or this distribution. Now, if there are more than this theta parameter, if there are more parameters, so parameters other than the parameter of interest theta, they are called nuisance parameter. which are not important for our this to be part of this exponential uh, function, which we have written here. Okay, so this is the general exponential family of distribution. So now we will take up several distributions and see how we can write those distribution, whether we can really write those distribution in the exponential family as an exponential family of distribution. And then we will check for several other distributions, other unknown distributions, some generalized functions, that whether they follow this exponential member of distribution or not, and whether if they are in the canonical form or not, what is the natural parameter, all these things we will do, because most of the questions in week 12 assignment is based on that. So that's why it's better to do that. Just a minute. Okay, so let's see. The first one, let us check for the normal distribution. First one is the normal distribution. For normal distribution, you have a for the random variable is u and a parameter called mu. Mu is here parameter of interest, theta, what we have written earlier, parameter of interest, and u is the random variable. Okay, so how we can write this normal distribution? It is known that it is 2 pi sigma square. This sigma square here, or the standard deviation sigma for the normal distribution, will act here as a nuisance parameter. Okay, so this is one of the example of the nuisance parameter. Parameter of interest is this mu, but other thing is the nuisance parameter. All right. So this is how we can write. So e to the power minus u minus mu whole square divided by 2 sigma square. Okay. So this becomes minus infinity. You can go from minus infinity to infinity. Now, how we can write it in terms of the exponential function? So we can write. Let us just put the exponential outside and write whatever is there within it. Okay. So first we let us write this as u into mu by sigma square plus mu square by 2 sigma square minus half log of 2 pi sigma square and minus u square by 2 sigma square. As you can see that, let me show here, this one exponential of, directly we have to write this, and this will be u square by 2 sigma square whole square, and so many terms will be there. Not so this will be u square by 2 sigma square, which we have written here, right? So it will be minus mu square by 2 sigma square. Another term will be mu square upon 2 sigma square. So that is already present here, right? And there will be a term where there will be 2 into u into mu, because we are just opening this bracket u minus mu whole square. So when you open the bracket, it will come out somewhere here where 2 will be cancelled out and you get u mu by sigma square. This is the term. And before this exponential function, there is another variable, not the variable, but is a constant, I would say, 1 upon root 2 by sigma square. That is written here as a log function. So now if you just operate this exponential function over this, you will get back this. So this is the rewriting of this particular equation within the exponential function. This is how we generally proceed for checking out the whether the distribution PDF is following the exponential distribution, or it belongs to the exponential family or not. Okay. So from here we will therefore compare with this particular equation, this one. We will compare with this and we'll say that, okay, your A of u is nothing but u say this one. This is not a parameter of interest, so I'm not worried about this. B of theta is nothing but, you can write mu by sigma square, does not matter. But this theta is here mu. Okay, so mu is the parameter of interest. We have to be careful. This has to be the parameter of interest. Next, P of theta, where theta is the parameter of interest mu only, which is nothing but minus mu square by 2 sigma square minus this bracketed term inside, half log 2 pi sigma square. Alright, because this only consists of mu, it does not consist of any u or random variable. So this is, so again theta is mu here. And finally, d of u, which has to be the function of u only, which is nothing but minus u square upon 2 sigma square. So we can clearly say that yes, it belongs to exponential family, right? And also, since a of u is equal to u, this is of the canonical form, and this is the natural parameter mu by sigma. This is what it is. So you can see that the normal distribution also belongs to the exponential distribution. But our thing is that when y will not belong to the normal distribution, all those distributions, whether they follow exponential distribution or not, then only we will be using the generalized linear model. In this case, we will not be able to use, because in this case, we can ordinarily use those multiple linear regression model, which we have done so far. Okay, assuming that epsilon or y belongs to a normal distribution. Okay, next is another distribution, second, which is binomial distribution. This is binomial distribution. Here, the binomial distribution, u is the random variable, p is the parameter of interest, is n cu p to the power u 1 minus p to the power n minus e. This is how the binomial distribution looks like. N is the total number of observation and U is 0, 1, 2 and up to n. Okay, so we can further write this as NCU P upon 1 minus P to the power U into 1 minus P to the power n. We can write this. And now the major thing, that is we have to accommodate it in the exponential term. So can we write? Yes. So the first term can be written as log of NCU. Second term, U log of P upon 1 minus P plus N log of 1 minus P. These are the terms which will be there. Fine. So now let's see whether this AU, B theta, all these things exists or not. So here, let's look at this term. You have a U and log of particularly this parameter P. Therefore, we can write that A of U is actually U, B of theta, which is here P, is nothing but log of P upon 1 minus P. Right? What about C of U? Oh, C of theta is N log 1 minus P. And what about D of U? Is nothing but log of N C U. So all these things following this kind of an exponential member of distribution. Therefore, this is also an exponential member. Okay, and also this is a canonical form. A of u is u. Okay, so binomial distribution also belongs to the exponential distribution family, and it is of the canonical form, and hence it can be used this whenever any data of response belongs, say y, any data belongs to this binomial distribution having some, say, u and p, then we can use the generalized linear model. Okay, so this is another distribution. Let's go for the third one, which is an important distribution, which is the Poisson distribution. So Poisson distribution, let us write this, how the PDF can be written. So it is f of u comma lambda, where lambda is the parameter of interest, is generally given as this e to the power minus lambda u to the power, sorry, lambda to the power u divided by u factorial. And you can go from 0, 1, 2, and so on to large values. Can go. So how can we write this as the exponential family? Just write exponential first and then accordingly you change. So this will be minus lambda because e to the power minus lambda is already present. Then what we can do is that u log of lambda, then minus log of u factorial. That's all. So let's look at this part. You can write therefore a of u as some u, b of theta which is equal to lambda is log of lambda. Well, c of theta which is equal to lambda again, theta is lambda here, is minus log of u factorial, and d of u is nothing but uh, answer. This is wrongly written. This is minus lambda, and d of u is nothing but minus log of u factorial. So this shows that this is also belonging to an exponential family of distribution and of a canonical form. Alright, so this is your third one. Let's go to the fourth one, another important distribution, which is gamma distribution. So in case of gamma distribution, let us define several things, say with theta parameter of interest and alpha as some kind of nuisance parameter. That means it is not a parameter of interest for us. So this becomes f of u comma theta as theta to the power alpha, u to the power alpha minus 1, e to the power minus theta u divided by gamma of alpha. This is a generalized expression where alpha comma theta is greater than 0, u is greater than equal to 0. Can we write this as some exponential number? Well, let's try. This is exponential. We will write and let's see what we can write further. So already we know that e to the power minus theta u exists. So we can directly write theta u here. Then all other terms will be accordingly changed. So this will be now minus alpha log theta, not minus, it will be plus because it is the numerator, plus alpha minus 1 log of u minus log of gamma alpha. That's all. So look at this parameter. It consists of u as well as theta. So a of u can be written as u, b of theta can be written as minus theta, c of theta can be now written as alpha log theta minus log of gamma alpha because this is only a function of the nuisance parameter alpha. Therefore, we can include it. And finally, b of u is nothing but alpha minus 1 log u. So again, this is again an exponential family of distribution, belongs to exponential family of distribution and of canonical form because a of u is equal to u. Now next is two more distributions are there, that is exponential distribution and negative binomial distribution. Let's touch upon that, and after that we will solve some practice functions and try to see whether they are also belong to the exponential family of distribution or not, and further we try to check whether they are of canonical form or not. And then we will proceed for fitting of the generalized linear model, and we will end up the lecture here. All right, let's go for now the fifth distribution, which is exponential distribution. Exponential distribution, as the name suggests, it should belong to the exponential family of distribution for sure. So, but let us still write. So, this is f of u comma theta is theta e to the power minus theta u. U is greater than equal to 0. So, easily we can write now exponential minus theta u can be easily written, and plus log of theta. That's all. Okay. So here a of u is u, b of theta is theta with a minus sign. Let's write it here. B of theta is equal to minus theta. C of theta is equal to say log of theta, and d of u is 0. Nothing is there. So it again belongs to exponential family of distribution. It might have that d of u is equal to 0, but if we can write entire thing with some known functions within this exponential bracket, then it is belonging to the exponential family of distribution. And also it is of the canonical form, as we have discussed in the earlier distribution. Fine. So this is done. And the last distribution, which is important, which is negative binomial distribution. So let's write about this negative binomial distribution. So the variance u is the number of failures observed to attain or successes in binomial trials with probability of success theta can be written as, so f of u comma theta is r plus u minus 1. Again, u will be the random variable, which is this number of failures observed to attain r successes. And as you can see, it will be some r minus 1, theta to the power r, and 1 minus theta to the power u. Quite similar to that of the binomial distribution, but the definition is somewhat different. Okay, so u is 0, 1, and so on. And can we therefore write this in terms of exponential? So let's see. Uh, let's look for the first term. So log of r plus u minus 1, pr minus 1. Next, r log theta. Next, u log 1 minus theta. That's all. So let's look at this particular term where you can see that, okay, here this r is kind of a nuisance parameter. You can clearly see it. Okay, so a of u can be written as u, b of theta can be written as log of 1 minus theta, c of theta is r log theta, and d of u is nothing but log of r plus u minus 1 c r minus, and of canonical, right? So this is also belonging to the exponential distribution. So whatever the essential thing is that whenever you have some kind of a distribution, you will try to write it in terms of this exponential bracket, whether we can generalize it with some kind of a log functions or known functions. After generalizing it, look for the variable consisting of the functions consisting of the random variable u and the parameter of interest theta together. Only term which consists of u as well as the parameter of interest theta is this one. Therefore, a of u and b of theta can be calculated from here. All other terms will tell you about whether it is b of u or c of theta. That's all. Once we can write to some generalized known functions within the exponential bracket, they all belong to the exponential family of distribution. If it is not, then it is not and this distribution cannot be written as the exponential family of distribution. And for the canonical form, just check this whether a of u is equal to u or not. So we will practice some question after this that will be much more clear. Okay, so these are some practice problems which we will touch upon now that will help you to solve all the questions of the assignment. And once we finish this, we will just briefly introduce about how to fit this generalized linear model, and that's all. Okay, so some basic simple questions are there. Question is that check most of the assignment questions or whatever questions which I have found in the NPTEL assignments and practice questions. These are related to the exponential, whether it belongs to exponential family of distribution or not, or whether it is of a canonical form or not. And simple link functions corresponding to a particular distribution, which we will discuss eventually. Okay. So check. Question is that check whether a density function belongs to an exponential distribution family or not. This is the question. So what is the density function which is given? Is this f of x comma theta, which is theta plus 2 x to the power minus theta. This is the question suppose which is given. So can we write? So what is the first step? First step is that we will always try to write this in terms of this exponential bracket. Can we write it? So no exponential functions are given in the density function. So we have to create our own. Some way we have to generalize to put it in this exponential bracket. Let's do it. So one is log of theta plus 2. We can clearly see. Another is minus theta log. Right? So next step is try to look for where you have the product of the random variable x and the parameter of interest theta. Only term which consists of this product of a function consisting of theta and a function consisting of x is this. Therefore, from here we can write a of, now the random variable is x, right? So a of x is nothing but log of x. B of theta is nothing but minus theta, right? Now, what about c of theta? Is log of theta plus 2. All right. So, yes, the question is, is it belonging to a exponential distribution family or not? We are finding out this, and d of x is suppose 0. So all these conditions are satisfied. We are able to write with some known functions this particular density function. So we can say that yes, it is it is belonging. It is belonging to exponential family of distribution. Right? So this question is over here. Now, next is it of the canonical form? Well, no. Is it of the canonical form? If this question is being asked, then problem arises that see our a of x is nothing but log of x, which is not equal to x. We want to have a canonical form only when a of x is equal to x. So it is not. It is not of a canonical form, right? So this is the one set of question which is over. Let's go for another question. Same. Let us have a distribution, say x comma theta, and not writing every time that the question is understood here, that it is theta minus 1 in to the power x minus 2. This is suppose another question plus 2. Okay. This is another function where theta is the parameter of interest and x is the random variable. So can again the question is same. Is this function belongs to the exponential family of distribution, number one, and is it of a canonical form or not? These two things needs to be checked. So step by step, go to the exponential. Can we write this in this exponential bracket? Well, let's see. Take the log, that is the best possible thing. So this is log theta plus log theta minus 1 to this is x plus 2 into log of theta minus 1. So what you can see is that a of x, this is the product term, right, is x plus 2. And b of theta is log of theta minus 1. Now, we can, of course, write this as, let's write it like this for the exponential. This is log of theta. This can be written as, see, x plus 2 into log of theta minus 1. So, can we write this as x log theta minus 1 plus 2 log theta minus 1? We can write, right? So, you can clearly see that this is the product. So, a of x is equal to x and b of theta is nothing but log of theta minus 1. C of theta consists of everything, log theta plus 2 log theta minus 1, and d of x is 0. So it belongs to exponential distribution and also it has a canonical form. Alright, so this is another question. Next is an important question. A similar kind of question you will get in the assignment. So, but it is from the practice set of question I have taken. So, here it is that a random variable x has following density function. So does it belong to exponential family of distribution? So this is the question which is there. So you will find that it is f of x 1 upon 2 to the power k by 2 gamma of k by 2 x to the power k by 2 minus 1 e to the power minus x by 2 where x should be greater than or equal to 0. Essentially a gamma distribution function. You can clearly see that. Now, again, step by step, we will go for this exponential bracket and we'll try to fit this particular thing. One exponential term is there. So finally, we can easily write minus x by 2. Well, next, plus k by 2 minus 1 log x, this term. Okay, next, minus log of 2 to the power k by 2 minus log of gamma k by 2. Let's see, the next thing is that can we see a term where there is a product of the functions of the random variable x and the some parameters of interest. So we can see that here it should be. So a of x, because this is a random variable, is log of x, and b of theta, which is nothing but k now, is k by 2 minus 1. All right. Next, c of x or c of k, because the parameter of interest, is this thing. Okay. So it's log of 2 to the power k by 2 minus log of gamma of a by 2, right? And finally, d of x is minus x by 2. So definitely, it belongs to exponential family of distribution, right? Now, next question is that, is it of canonical form? Well, quite clearly, ax is equal to log x, which is not equal to x, therefore, not of a canonical form, not having canonical form. Done. Next question related to this: what is the natural parameter? So natural parameter, we have defined that it is nothing but b of theta. Here is still it is b of k, which is now k by 2 minus 1. This is the natural parameter. Okay, so this is the answer for all these practice questions. Okay, essentially in the week 12 assignments, we'll get mostly this kind of a question and some questions related to the link function, which we will cover after this. How to flip the functions, the generalized linear model, and a brief introduction I will give, and then we will talk about the link function. It is related to that only. Okay, so now we will move to the fitting of the generalized model. But before that, some small topics are left, which is the expected value and variance of the above distribution having A of u. Okay, so how to calculate this? So expected value of A of u is nothing but minus C. This dash represents first derivative with respect to theta, and this is b prime theta. Okay, and variance of AU is nothing but double derivative of theta, c prime theta. Sorry, this will be a function of theta, but it will be with respect to u. Okay, so d dx d du actually. Okay, this minus e double prime theta and b prime theta. Just for the, if sometime it is required, we can use. Okay, this to the power. That's all. So these are some few things which are there. Well, any other things are there or not? Let me see. Okay, so I think this is enough. Let's go for now fitting of the generalized linear model. Just a minute. So start with, suppose we have a set of independent observations, that is yi is the response and xi prime. This is nothing but a transposed vector. I goes from 1 to up to n. N observations are there, right? So what is this xi prime represent is that xi1, xi2, and so on up to xi. Just like what we have done for, if you remember, for the multiple linear regression model, we have taken this p as k minus 1. Here we are talking about only p. There are p unknown parameters. That's all. That is what we are trying to say here. Okay, this is a kind of a multiple linear regression model. So these are nothing but the regressors. Okay, these are nothing but the regressors. X0, x1, x2, so on. And I represents the ith observation. There are n observation. The ith observation is xi1. Well, now yi is from, as we have discussed earlier, from some exponential type distribution. Not only that, with canonical form. It should exist, otherwise we cannot use. So y should come from an exponential distribution. It should not be a normal distribution, because normal distribution we have seen how to do that in the earlier lecture. If the y is not from a normal distribution, but it still belongs to some kind of an exponential type distribution with canonical form, that is a of x should be x, or whatever the random variable is, then for that we can use this generalized linear model. So canonical form is a of y should be equal to 1. That's the thing, because y is the random variable. So for that, your joint PDF you can write, means joint PDF means with x and y and all the parameters theta and all. So you can write y x1, x2, so on up to how many xp, right? And finally theta and phi. Just a minute. Let me check whether I have written it correctly or not. I think it is fine only. Yeah. Yes. Okay. So these are the terms theta and phi. This can be written as, I think this will be some y1. This is some y2 and up to some yn. Because we are talking about the random variable, not the x. X's are not the random variable. So y1, y2, y3, because all these distributions y1, y2, y3, so on up to yn, each are the sample observations, but this belongs to some kind of a distribution. We have discussed it earlier. Okay, so these are all the functions of y. So this is to be written like this: summation in I yi b of theta. Because why am I writing this? Because this is a of y. Okay, and then summation I p of theta I, and finally summation d of y. Okay, same thing, same exponential member we have written here. Only change I have done is that this is yi into d theta. Yi I am writing because it is of the canonical form. That's why you can write this. Okay, and of course, theta is the parameter of interest. Phi is Newton's parameter, like sigma square, which we have seen in the normal distribution. Okay, this is the Newton's parameter. Theta is the parameter of interest. B theta is the natural parameter. So parameter of interest, right? And of course, your beta is beta 1, beta 2, so on up to how many parameters? There are three parameters are there. So this is your beta matrix. Okay. So what we need to do is that we have to we have to find some suitable link function some g, which is some function. So g of mu I is equal to xi prime beta. Just what we write in the multiple linear regression model, that y is equal to x beta. Right. So in the multiple linear regression model, we generally write xi prime beta plus epsilon, and e of y I therefore is nothing but xi prime beta. We have discussed this because e of epsilon is 0. This is for the multiple linear regression model in general. But here, since it is not from the normal distribution, we are writing some g of mu is equal to xi prime beta. That is, g of expectation of yi should be xi prime beta. This is the difference. Instead of expectation of yi, it will be some link function of expectation yi. That's the difference. Okay. And so g is what? So I've defined, but still again. So this is nothing but the link function. And you will see that this link function is nothing but the natural parameter, generally considered as the natural parameter. We will write it later. So this is the main thing. So main condition again, I will repeat this error distribution epsilon or response distribution must be a member of exponential family, right? So given yi xi prime, which we have seen, we you may not give this transpose; it does not equal. We want to explain the variability of yi in terms of xi. This is what we generally do in the regression model. So the problem is that the distribution is not normal. So problem is distribution is not normal in this. So how to fit it? For fitting, so therefore for the fitting, as I have already shown, so the variation in yi or expectation of yi, which is nothing but the theta I, which we have seen in the normal distribution as the mu, the parameter, okay, parameter of interest, can be explained in terms of this xi vector value. Let us see it. So we can write or find a link function, in general link function g of theta I is equal to xi, and to right travel or not, it depends on you which way you are writing the matrix. So g of theta is xi prime beta. So as I have already mentioned, this link function is often the natural parameter. Remember, this natural parameter is also a function of the parameter of interest, b theta. Okay. So this is the thing. So for normal distribution, it is already known that it is nothing but the mu for normal distribution. So g of theta is nothing but theta. So we write y is equal to x prime beta, which we have seen. This is for the normal distribution. But for other cases where y is not a normal distribution, in that case, then what will happen? Say, suppose, let's talk about binomial distribution. for the binomial distribution, you have we have seen that g of theta is nothing but log of theta I divided by 1 minus theta I. This we have seen if you go to this the p of theta for the binomial distribution. See, this is log of p upon 1 minus p. So that is what we have seen it here. We are writing the same thing, right? This is the natural parameter for the binomial distribution. And we then write that this function, this log of theta I upon 1 minus theta I is nothing but xi prime beta. And then solve. But this solving should be done using maximum likelihood estimate, which is a big concept. So I am not going to touch upon that. So this is therefore theta I can be written as from this and this you can combine and write xi prime beta divided by 1 plus exponential of xi prime beta. Further, you can write this as now in terms of the known things, known expressions. Suppose theta is equal to p, where so yi is of the form for the binomial distribution of the form ri. This is a success and this is the total ni, right? So ri is the number of successes in ni trials. This is how this binomial distribution is defined. Okay, so each having probability, probability pi. So we can write that log of pi upon 1 minus pi is xi prime beta, and this xi prime beta can be written as beta 1 x11 or I1 plus beta 2 x I2 so on up to p parameter beta p x I. This is how it has to be done. Similarly, if we look for the Poisson's distribution for the second case, suppose for the Poisson's distribution, this is f of, as we know that this mu I. This mu is actually lambda. We have defined it as lambda. So anyway, we can write this as y log of mu minus log of y factorial. So this is the thing. So b of your theta, which is nothing but b of mu, is nothing but log of. So this will act as your g, a link function. This will be my link function. So we can write this now log of mu I is equal to xi prime beta, or mu I will be equal to exponential of xi prime beta. Right. So this is how we can write. And what is this? So E of yi, expectation of the y distribution is this. So can be written as this xi prime beta, which is y. Right. So this is exponential. So just so this is fifth classified and you can write for the actual model. So this is how this link functions can be established. So let me just give a list of all those link functions corresponding to each distribution. So the distribution, okay, the link function g of theta, the natural parameter, which is the same. Okay, so the first one is normal, which is not of our interest for this case. So g of mu is actually equal to mu. Number two is binomial, which we have seen that g of p now is nothing but log of p upon 1 minus p. This is sometimes called the logistic. logistic link. Third is Poisson distribution, which we have seen, g of lambda or mu, whatever you wanted to write, log of mu. This is log link. Next is the exponential distribution, where g of mu is 1 upon mu. This is, say, it is called reciprocal. And for the fifth, the gamma distribution, g of mu is same, 1 upon mu. This is also reciprocal. So these are few distribution and their link functions. So this is nothing but the link function. So based on that, you can really solve all the assignment questions, I guess. Okay. And one last thing, in order to estimate all these relationships or finding the coefficients beta 1, beta 2, beta p, people use maximum likelihood estimate. More details are there in the week lectures, so you can follow that likelihood estimates to calculate this calculate the betas. So for that, the likelihood function has to be made, which is nothing but that exponential function which we generally write yi. So for the binomial case, so this is p upon 1 minus p, and write I also, plus summation a9 log of 1 minus pi plus summation log of a9 pyi. And the next thing is that we take log of this. So exponential will be gone, yi log of pi upon 1 minus pi plus a9 log of 1 minus pi plus summation log of a9 py. And finally, what we have to do is that we have to maximize this function. Maximize log of L with respect to all the betas. So you have to first differentiate with respect to beta 1, then beta 2, and so on up to beta p. This will give you several equations. Solving them, you will get these coefficients. Just like what we have done for the linear regression, simple linear regression, or multiple linear regression. Several normalized equations we will get similar thing. Only things that we are using a different function called the likelihood functions and taking its log and maximizing it. So these are the uh, uh, things which I wanted to discuss today. Mostly this will be an important part, so I just highlight whichever things are important for the solving the assignments and for the concepts. This is important. Which distribution is for what? Particularly these couple of things are fine enough. And we have also seen to fit this generalized linear model. When we are using this generalized linear model is important. Also, these practice questions are important. Uh, Exponential family of distribution. So this is one of the criteria for uh, applying this generalized linear model. Not only that, the y distribution should be from the exponential family of distribution, but it has to be of the canonical form. If the canonical form does not exist, then the link function will not exist. So whatever functions we have or distributions we have discussed, they all have canonical form. We have seen that. That's why the link functions exist. So these are the couple of conditions which are important. And yes, so it should not be from the, we are using this generalized linear model only when the error distribution is not from the normal distribution. That's all. And we have solved this assignment question. So I think this will be enough to solve the questions for the week 12. I think we can stop here. If any question is there, we can. So any questions? Okay, if there are no questions, then I can stop here. We will meet next week then.